Hello, in this video of refrigeration and air conditioning, we are going to learn about vapor absorption refrigeration systems. They are alternative to vapor compression systems, but they have existed way before vapor compression systems. So, as I said, they are the oldest method of producing refrigeration effect. They were discovered by Michael Faraday in 1824 while experimenting to liquefy certain gases. The first vapor absorption refrigeration machine was developed by a French scientist named Ferdinand Care in 1860, which can be used in both domestic and large industrial refrigerating plants. The refrigerant used is mainly ammonia along with the water. Also, the compressor part of the standard vapor compression cycle is replaced by an absorber, pump, generator, and pressure reducing valve. It uses heat energy to change the required state of the refrigerant instead of compressing it. So in this video, we are going to learn about simple vapor absorption system, then lithium bromide vapor absorption system, Electrolux vapor absorption system, its applications, and comparison of vapor absorption system with vapor compression cycles. So this is a case schematic of simple vapor absorption system. As you can see, there are standard components from the vapor compression systems, that is condenser, expansion valve, and evaporator. So refrigerant, in this case which is ammonia, comes into condenser in the form of high pressure vapor. It cools down and converted to liquid refrigerant, that is liquid ammonia, by rejecting heat to the surroundings. Then it is passed through expansion valve where the pressure and temperature is reduced. Now this low temperature and low pressure liquid ammonia is supplied to evaporator where it absorbs heat from the surrounding for producing cooling effect and converts the refrigerant to low pressure ammonia vapor. So phase changes from liquid to vapor by absorbing the latent heat from the surrounding. Now this low pressure ammonia vapor is supplied to the absorber. So from 0.6 to zero point 0.1, the cycle is exactly like the vapor compression cycle. But we will start the whole cycle explanation from point 1 again. So, which is different in vapor absorption cycle. So, from point 1 receives low pressure ammonium vapor leaving the evaporator. This vapor is passed through absorber where there is a weak solution of water and ammonia, also known as aqua ammonia solution. So, weak aqua ammonia solution is there in absorber, which is further cooled for increasing the holding capacity of water or dissolving capacity of water for ammonia. So the solubility of ammonia increases and hence more and more maximum possible amount of ammonia is dissolved in water, in cold water, in the absorber. So the weak solution which is here, or the less amount of ammonia in the water which is here, is converted to the strong solution, means there is a maximum possible ammonia is dissolved in the water in the solution. So strong aqua ammonia solution then exits the absorber and passes through the pump, where the pump pressurizes this solution up to 10 bar using the external work. Here we need to provide electricity to the pump. So pump provides pressure to this strong solution and supplies it to generator. In generator there is an heating arrangement. So heating coil heats the strong aqua ammonia solution, thereby reducing its solubility, that is holding capacity for ammonia. So ammonia vapors are released in the generator. So for the namesake, generator generates the ammonia, and this ammonia is in the form of high pressure ammonia vapor because of pump, and this high pressure ammonia vapor is passed to the condenser. This leaves high pressurized but weak ammonia solution inside the generator. This weak ammonia solution flows back to the absorber through a pressure reducing valve, so that mixing does not cause a problem. The high pressure ammonia vapor from the generator is passed through condenser where it follows its usual cycle, that is expanding in expansion wall and producing cooling effect in evaporator. This completes the simple vapor absorption cycle. So you can see that from point 1 to 5 there is a small internal cycle of strong and weak solution where the weak solution in the absorber converts to strong and pumped to the generator where it again reduced to weak solution and passed through the absorber. So this is a small cycle of aqua ammonia, and after this point from 6 to back to 1 there is only ammonia as a working fluid inside the solution or inside the refrigerator. So ammonia acts as a refrigerant and water is solvent for this ammonia. Now this aqua ammonia solution has some desirable properties of refrigerant absorber mixture. Mainly aqua ammonia solution is the only solution which passes on all these criteria. Let us see what they are. The first is it must have more than Raoult's law solubility. That means it should be create a strong solution highly rich in the refrigerant which is formed in the absorber by absorption of refrigerant vapor. As we have seen, it should contain highest amount of refrigerant inside the solvent. Then refrigerant should have high affinity for absorber at low temperature and less affinity for the absorber solution or the solvent at high temperature. So this makes possible for creating a strong solution in absorber and creating a weak solution in generator which can generate vapors back. Then should have large difference between the boiling points of two components of mixture. That is, in this case, the ammonia and water must have large boiling point difference, at least 200 degrees Celsius. This ensures that almost absorbent-free refrigerant is boiled off of the generator and absorbent alone returns to the absorber. This is not exactly followed in aqua ammonia solution. We will see the effects and solutions for this afterwards. Then the solution must have low viscosity to minimize the pump work. If there is refrigerant absorbent solution which is very high viscous, then the pump will have to work more and will consume more electricity. It should have low freezing point, so it should not freeze inside the system, thus causing the damage to the system. And it should have good chemical and thermal stability. It should not corrode or erode any parts of the refrigeration system. It should be non-corrosive. This is the performance evaluation, that is calculating the coefficient of performance of the simple vapor absorption system. So COP is desired effect upon the input energy provided. So here desired effect is heat absorbed in the evaporator, which is our cooling effect of the refrigerant. And the input energy provided is work done by the pump and heat supplied in the generator. This can be represented in symbolic format like QE. QE is heat absorbed in the evaporator, QG is heat provided to generator, and WP is work done by the pump. If you see the values of QG and WP, it is often seen that WP is negligible with compared to QG. So COP is approximately considered as QE upon QG, where QE is heat absorbed in the evaporator and QG is heat supplied to the generator. So now according to first law of thermodynamics, QC is equals to QG plus QE. So QC is heat rejected to the atmosphere must be equals to heat input to the system, that is heat absorbed by the system. So system absorbs heat in two places, generator and evaporator, and rejects heat into one place, that is condenser. So heat rejected by the condenser must be equals to Qg plus Qa, that is heat input or heat absorbed by the system. Now let us consider these 3 points, that is generator, evaporator and condenser have 3 temperatures. We are obviously seeing this for ideal cycle. So let us assume that there is a constant temperature in the generator at which the ammonia vapors are generated. There is a constant temperature in condenser in which phase change process is taking place, and the heat is discharged to the atmosphere or the cooling water. Let let us consider TE is the constant temperature in the evaporator which is absorbing heat from the environment and converting the ammonia liquid into ammonia vapor. So since we have this equation and it is considered to be perfectly reversible system, the entropy of the system, initial entropy of the system must be equals to the output entropy of the system. That is the entropy in the generator, that is Qg upon Tg is equal plus Qe upon Te. This is all initial entropy must be equals to final entropy of the system, Qc upon Tc. This is for condenser, this is for evaporator, this is for generator. In both this we are absorbing heat, in condenser we are rejecting heat. So using the equation we have stated before, this one, we will now expand this formula. So Qc can be written as Qe plus Qg, which we have already seen by energy balance. Now just rearranging this. So this Tc is given separate and it is exchanged. So after rearranging you get Qg in terms of Qe and temperatures, and finally after some cancellation like Tc is getting cancelled here and some altercations, changing of the plus and minus, changing of the sequence of the minus, if both of these are changed, both of these are changed, after that you get Qg upon Qe, or as we have defined the COP is Qe upon Qg, so we will get a final equation of vapor absorption cycle which is considered as isentropic and perfectly reversible. So this is the maximum coefficient of performance which is possible in vapor absorption cycle, which only depends on 3 temperatures, that is temperature in evaporator, temperature in generator and temperature in condenser. So this is the formula for maximum possible coefficient of performance of vapor absorption cycle. Obviously, due to some practical factors, this is not achieved. The real or the actual COP is some percentage of this. We will see one small numerical on simple vapor absorption system next. So in an absorption time refrigerator, the heat supplied to ammonia generator by condensing steam is at 2 bar and 90% dry. So this is heat input. This steam is the heating part of the generator. The temperature in the refrigerator is to be maintained at -5 degrees Celsius. This is temperature in the evaporator. Find the maximum COP possible. Formula we have just covered. If the refrigerant load is 20 tons and actual COP is 70% of the maximum COP, find mass of the steam required per hour. Take the temperature of atmosphere as 30 degrees Celsius and assume the only latent heat of steam is used for heating purposes. So whatever the latent heat of steam is at that pressure and temperature, that will considered as heating part of the system. And here it is given that actual COP is 70% of the maximum COP. So let us write the given of the system. So pressure is 2 bar, X, that is Raynaud's fraction is 90%, which is 0.9. Q is 20 TR, required refrigeration effect. TE, temperature in the evaporator is -5 degrees Celsius, obviously in the Kelvin. Then temperature of condenser is maintained at 30 degrees Celsius, that is given because condenser rejects the temperature, rejects the heat at atmospheric temperature. So therefore condenser temperature will be 30 degrees Celsius in Kelvin 303, And one more factor is given, actual COP is 0.7 of the theoretical or maximum. This is also maximum COP possible. So let us go for this by step. First, we need to find the properties of steam at 2 bar, X is 90. So saturation temperature of steam at 2 bar is 120.2 degrees Celsius, which is converted as 393.2 Kelvin. So it is given that only the latent heat of the steam is used. So we will consider Tg, the temperature, as equals to the saturation temperature. And latent heat of steam at this point is this. We will need this for heat input. So let us start. Firstly, we have all three temperatures now, TE, TC and TG. So we can find the maximum COP by just putting the values. It is 1.756. Now you need to find the actual COP using this 0.7 wala. So the actual COP is 0.7 into theoretical COP. So that is 1.229. I have just multiplied the 0.7 to the 1 point. Here there should be a point. A point is missing. Okay. So this should be the actual COP. Now from actual COP, you can find the actual heat supplied. So refrigeration load is 20 TR. We can convert it into kg per minute. And we can divide it by actual COP. So actual heat supplied, refrigeration load upon actual heat supplied will be actual COP. So this will give us the heat supplied. And this heat supplied will be equals to mass flow rate into latent heat per kg. So mass into latent heat per kg is heat supplied, and using this formula we can get 1.552. So both of these are just logic questions. The last two parts we are going to find. This uses the formula we have learned in vapor absorption system. I hope this clears the sum for you. Now we will see practical vapor absorption system. So what does this mean? There are three additional components in the practical vapor absorption system, and they are very essential. The first one is analyzer, then there is a rectifier, and then there is a heat exchanger. So if you remember, the evaporator, expansion valve, condenser, generator, pump, pressure reducing valve, and absorber are nothing but same with the previous vapor absorption system we have studied. This just uses three extra components, that is analyzer, heat exchangers and rectifier. So we will see their functions one by one. So firstly, analyzer. Analyzer is just installed after the generator. Now in our simple vapor absorption system, the strong solution from the pump is directly provided to the generator. Here it is first passed through the analyzer. Here the strong solution is already at higher pressure due to the heating from the pump and additional pressure and the heat exchanger, which we will explain afterwards. So this is, at this point there is an high pressure hot solution. So some ammonia vapor is already leaking out of this. So this ammonia vapor passes through rectifier to the condenser. So this ammonia vapor is given out, and whatever the solution is left, which is weak, is condensed and it drips down through the analyzer to the generator. So it becomes part of the weak solution here. Again, this weak solution is separately supplied to the heat exchanger and it goes down the pressure reducing valve to the absorber. Now, sometimes from this high pressure and high temperature weak solution, a strong solution, ammonia vapor carries water vapor along with it. For converting this water vapor back to the water and dripping it down to the analyzer, we use rectifier. But analyzer is like a distillation column, it just contains alternate horizontal plate. We will move to the rectifier. So when water vapors are not completely removed in the analyzer, rectifier is used. It is kind of dehydrator or a cooler which cools the water vapor and drips down the remaining water through analyzer to the generator to create the weak solution part. So both rectifier and analyzer together ensures that this part, condenser input part, is only high pressure ammonia vapor and there is no water vapor present in that. Water causes freezing inside the evaporator if it is passed above the condenser. So that creates the problem for the whole system. Therefore, both rectifier and or dehydrated it is called analyzers are used. As for the heat exchanger, they are used for improving the performance. Now, Now, as for the heat exchanger, they are means of improving the overall performance of the vapor absorption systems. So there are three essential components which are extra in practical vapor absorption system, out of which we have seen the analyzer and rectifier, which is solely responsible for passing only ammonia vapor to the condenser. But heat exchanger is used for improving the performance of the overall vapor absorption systems. So it is used between the pump and the generator as seen here. This is what we are talking about, this heat exchanger. So it contains two lines. One is the weak solution which is leaving the generator and going towards the pump reducing pressure reducing valve, and the other one is the pumped strong solution which is going to the analyzer. So what is do is the weak solution is at higher temperature because it is coming out from the generator which has heating coil inside it, and generators basically heats the vapor for generating the ammonia vapor, which passes through analyzer and goes to condenser as we know. So this weak solution is high in temperature, whereas the strong solution is high in pressure from the pump but at lower temperature than the weak solution. So what happens in the heat exchanger is that weak solution rejects the heat to this strong solution, which is anyway needed to be heated in the generator. So this reduces the heating requirement in the generator. The strong solution is heated by absorbing heat from the weak solution. So it gets weak solution to cool. Thus, the cooled weak solution passes through pressure reducing valve back to absorber where it is cooled again for absorbing more amount of ammonia. So absorber receives the cooler solution than it would have been receiving before. So also reduces the required cooling effect in the absorber. And the strong solution is heated and passed through analyzer where at this point it can generate more ammonia vapor. Now it is both high temperature and high pressure somewhat with compared to the previous things. This results in ammonia vapor going to the rectifier and the weak solution or the water solution of ammonia drips down to the generator where it is heated again to generate ammonia vapors and the cycle goes on. So this heat exchanger reduces the heat requirement in the generator. Vapor absorption system can work on the waste heat for this generator. It is basically using a low grade heat energy. So it can be used for regeneration and it can be used for on waste heat. So this is effective. So that's it. We have seen now simple vapor absorption system, the requirement of the aqua ammonia or binary solution of absorbent and refrigerator in simple vapor absorption system, and we have covered practical vapor absorption refrigeration system which consist of three additional components to the simple vapor absorption system, that is rectifier, analyzer and heat exchanger. So this concludes this session and we will see the lithium bromide absorption system, electrolux, which are the variations of vapor absorption system in the next session. We will simultaneously see the applications of the vapor absorption system and compare it with the standard or more commonly used vapor compression system. So thank you. I hope this video helps your understanding in vapor absorption systems of refrigeration as compared to the most common types, that is vapor compression systems. So goodbye and thank you.